It looks like everybody's late today, other than Sunandan.
Yeah, it's okay. I mean,
You're right. Oh. Oh. That's all right. Back to what seriously, that centre played really good. I would
so,
like.
yeah, I don't know what's happening. I've managed to play something. Sorry, are you all there? I'm trying to start the recording.
Yes.
Yeah, okay. So just let me start the recording and then I really don't know what to do. I just press some buttons in some random order and each time it works. Something is happening. Okay. Yeah. So, good. So maybe we'll start. Good morning. So our plan today is to continue with these somewhat geometric aspects of linear programming about polytopes. Yeah. So what we will do is we'll talk about polytopes a little bit more. There was a decomposition theorem that I mentioned last time. We will derive that decomposition theorem. And then there are some, what I thought, very wonderful applications of these convexity type of ideas. And I wanted to show you one proof, which I saw only recently. And this is Zacarias' proof of Tverberg's theorem. And I'll tell you about it at the end. So I hope we can get there. But please keep asking, stop me. There is no hurry. Okay. Yeah. Okay. So to begin with, are there any questions? There is anything particular about last time that you would like to cover? Let me know. Otherwise, my plan is just to review the theorems. I'm not going to review the proofs now. Okay. So I'll continue, but I hope today you will interact more. You will ask me things. Okay. Okay. So the main theorem, and this is a very important theorem, and it is intuitive. So let us just review it. So this is the fundamental theorem of linear inequalities, and it's about cones. Okay. So suppose you have a finitely generated cone. That means there are some given vectors a1, a2, an. You should think of them as some rays. And then there is a cone they generate. And either this vector b is in the cone, yeah, it is in this cone, or there is a hyperplane with its normal pointing in this direction, and the entire cone, the very same cone, is this side, and this b is on the other side. Okay, strictly on the other side. Yeah, look, this thing is a strict inequality, and all these are on this side. Furthermore, this cone, we can assume, rests on this hyperplane. So for example, when you draw a polygon, yeah, so let me draw it. So and you have a point outside. Or maybe some other point. Let me just. So, I mean, what is the connection with the cone? We will very soon see how polygons and polytopes are related to cones, but the way you should think about it is this is drawn on this plane, but we are actually one dimension above. So the tip of the cone is maybe outside, and the cone is going down into this polygon. Yeah, the cone is going into the screen. Yeah, and this point is also becomes a ray. Yeah, because you have chosen your origin outside the plane. Okay, then from our old plane intuition, we know that either this point is inside the polygon. If it is not inside the polygon, then there is some sort of a line which separates them. But actually, if you think about it, one of these lines, one of the edges of the polygon itself, yeah, when extended, must separate them. Now here, this looks like a line which is not passing through the origin, but the way you should think about it is that this line, together with the origin, which is outside, yeah, you connect this line with that origin, that will form a plane. And that plane has this cone, because this polygon has turned into a cone on one side and this point on the other side, and that the cone is resting on this. So now you have m-1 vectors. Yeah, these points have turned into vectors now. Yeah. So m-1 linearly independent vectors which describe that plane, and this point is on the other side. So that is the content of the second part. Yeah, so whenever you have this situation where this point B is outside, you can find such a hyperplane. Okay. So that is where we were. Yeah. So any questions about this? Yeah. Now, last time we talked about cones in general. Yeah. So these are objects like this. Sometimes even half spaces are cones. Now, there are two ways of thinking about cones. Cones can arise in two ways. One is, these are polyhedral cones. That is, you just take some half spaces defined by hyperplanes which are passing through the origin, yeah, and take their intersection. This is the intersection of half spaces. That is, some inequalities are being satisfied. Okay, and if a point is in this cone, any non-negative multiple of that point will also be in this cone, because each of these equations, yeah, if you multiply by a lambda, it will continue to hold. Okay. Yeah. So if this x satisfies this, if you multiply x by a lambda and lambda is non-negative, all these inequalities will continue to hold. Yeah. So that is a polyhedral cone. On the other hand, the kind of cones that we just discussed, where you were given some rays and you just said, I will take all conic combination. Conic combination means non-negative linear combination. All the coefficients that you have to choose have to be non-negative. So non-negative linear combinations, conic combinations, you put them together and what you get is this cone. So there are two ways of defining a cone. Either you could define it using inequalities, or you could define it explicitly using some rays which generate it. Okay. And in both cases, the number of inequalities here, something is finite. Here the number of inequalities is finite. Here the number of points given is finite. Yeah. And there is a related object which we will discuss and which probably is more familiar to you. The right hand side here, instead of being 0, yeah, is some vector which can be positive, negative. Yeah. So then the solution here becomes, a polyhedron. Yeah. The plane, the half spaces don't necessarily pass through the origin, and then it becomes a polyhedron. It can be an unbounded polyhedron. Okay. Yeah. So then such an object is called a convex polyhedron. On the other hand, something analogous to this, yeah, is called a convex hull. So what you do is you take these points that generate the convex hull and you take all convex combinations, meaning you take their averages. Okay, all possible ways of computing their averages with various weights. Okay, so this is convex hull. So we have discussed that the main theorem, yeah, sorry, yeah, was that if you describe the cone using points, using its rays and taking all conic combinations, the very same cone can also be described by inequalities. Yeah? So if a cone is finitely generated, there is a finite number of equations, inequalities, that define it. And the opposite, if there is a finite number of inequalities that define it, then there are finite number of points which generate it. Okay, yeah. So the way you should think about it is, when you are given those rays, then the rays tell you what to include, yeah, in the following sense, that any point which can be generated by those rays, yeah, they provide you, I mean, those are in the cone. Yeah, anything that can be obtained as a conic combination of the rays is in the cone. Whereas when you have these constraints, yeah, ax less than b, any point which violates any of those inequalities is not in the cone. Okay, so suppose somebody gives you a point and claims that it is in a cone. Okay. It is in the cone. Then one thing they could do immediately is they could say that, look, these were the points that were generating the cone, and here is this point which can be expressed as a linear combination of these points which generate. On the other hand, if something is not in the cone, how do they convince you that it is not in the cone? Well, if they also had the equations, yeah, the inequalities which define the cone, they could point to a particular inequality and say that, look, this inequality certifies that your point is not in the cone. Okay. Yeah. So in each case, you have to solve one equation. For points in the cone, you just verify that the weights given by this person who is claiming that the point is in the cone, they in fact work out. Okay. And if the point is not in the cone, you again study one inequality which has been pointed out by this person who is claiming that the point is not in the cone, and you just verify. So these are related to ideas about, you know, NP and co-NP. Yeah. And right now we will not discuss it, but yeah. So
in the previous slide, so a convex polyhedron can be unbounded, right? But
convex polyhedron can be unbounded, yes.
But isn't the convex hull of a finite set of points always bounded?
It is always bounded. So we will soon tell what is the relationship between convex polyhedron and convex hull. We will just come to that. Yeah.
Okay.
So I'm not claiming that these are equal. They are related. Let us see what they are related by. Okay. Yeah. So in this case, they were equal. In this case, maybe I said they are equal. I just meant to say that they are related. Let us see what. So in particular, what we will end up proving is that if this is also bounded, if a convex polyhedron is bounded, then it is a convex hull of a finite number of points. So that is one of the things we want to prove. Yeah, good. All right, thank you for the question. Others should also ask. Yeah, please. So the thing I want to prove now is that if P is a polyhedron, then P can be written as a sum of two objects. Now, some of you may not be conversant with this notion of taking sums of objects. Okay, so Q is a convex hull of a finite set of points. C is a cone. So both of these are sets of points. This is one set, this is another set. What do we mean by the sum? By the sum, we mean you take a point from here, take a point from here, and add it up. Okay, so maybe we should, I will soon do an example, but maybe I will, yeah. So maybe tell me if this was in this year's entrance exam.
So the notion of sum is similar to that of vector spaces only, right?
Let us see, it is similar. Yeah, so look at this, and suppose I have this. Yeah. So this is one object. Let us call this the object A and this object B. And let's put an origin everywhere so that, yeah. So so every point here, yeah, with respect to this origin. Now, what is A plus B? Yeah. So you take this point with every vector here, let's see if I can do that. Yeah. How do I do that? Yeah. Okay. Yeah. So I with every point in this, I add this little circle to it. If I add this circle to it, then I start getting these points. Yeah. Then I should have proved. Okay, let me start again. Yeah. So then I move this circle all over this square everywhere. Okay, and all the points that I am able to reach, that becomes the sum of A and B. Is that clear? So do you see what the picture will look like? Yes, so let me just place it here. Yeah.
Ellipse.
Ellipse. Yeah, just think about it.
Circular cornered square.
That's right. Rounded squares. Yeah. So in all your drawing software, when they ask you, do you want a rounded square? Yeah. So this is what they mean. This will be, maybe a square like that with a rounded corner, square, rounded corner, square, rounded corner, sorry, straight line, rounded corner. Is that clear? Yeah. Suppose you have a polygon with k vertices and another polygon with r vertices, and you move this polygon over this polygon. Yeah. You will get a polygon again. Yeah. And I let you convince yourself that it will have k plus r vertices. Yeah. Or something like that. Yeah. Yeah. So the notion of sum is clear. Yeah. It is like vector spaces, but from each, you take a vector from one, take the vector from the other, and add them up using the usual law of vector addition. Nothing special about addition. So now what is the claim? When you take a polyhedron, it will consist of a polytope, a convex hull of a finite set of points, and it will be a cone. Yeah. So maybe I will draw something here. So when you take a bunch of a polyhedron, right? So you have drawn some inequalities, and something comes out of those inequalities. So you wrote the first inequality. Let's say this was the first inequality, and you're looking at all the points which are on this side. Yeah, this is the first half space. Then you got the second half space, and let me just say that again the points are on this side. Yeah, and then maybe let me not make it too fancy. This half space. Yeah, and this space. So now let me stop here. So what has happened? This is a polyhedron, which the shaded area is a polyhedron. Now this polyhedron, I'm claiming maybe, yeah. So it is a sum of a polytope And should I do one more? Okay, let me just stay with this. Then I will do a slightly more complicated example or different example. Okay, yeah. So this is a polytope. Now the claim is, sorry, this is a polyhedron, and the claim is that this polyhedron is a sum of a polytope of a fine, yeah, and sorry, sum of a convex hull of a finite number of points and a cone. Okay, so let us see which are those. So if you look at these 2 points and look at their convex hull, what is their convex hull? Their convex hull, say, is this. Yeah. So it is this convex hull. And now, which cone am I talking about? I wish I could draw properly. So this is your origin. Draw a line parallel to this. Draw a line parallel to this. Yeah. Parallel to this, and yeah. So one line is parallel to this, another line is parallel to this, and consider this cone. Now, do you see that if I move this cone, it's tipped on this polytope? What will I get? When I place this tip here, I'll get this. Then as I move it down, and I will have generated the whole polytope. Is this clear? I'm saying all kinds of nonsense words. I would have generated the whole polyhedron. Is this clear? Is there a question? This is just an example. Okay. Now, let us just make it slightly more complicated, let's say. Yeah. So suppose there was one more half plane. No, not like that. Yeah, I don't know, my lines are all slipping, but so let me just try. Something like that. And I again have this yeah, but this time I have this. Okay. Now, in this case, when I try to do this same thing, I will get this finitely generated object generated by these 3 points together with a slightly skinnier cone. Yeah, the cone will consist of this line and this line, these 2 lines. Okay, so it will probably be, I'm not drawing it at the same place, it will be something like that and something like that. Okay, yeah, this part. And if I move that, but now I have to move it over the entire convex hull. Yeah, I cannot just move it over this line as I did before, because now our convex hull is this. Okay, so with this sort of some feeling for what polyhedra look like, let us review this claim. Any polyhedra has a finite part, which is a bounded polyhedron, which is generated. Yeah, we explicitly say that it's a convex hull of a finite set of points, and it has an unbounded part, which is described by a single cone. Okay, and that cone, when moved over this polytope, generates your polyhedron. When moved over this convex set of points, generates the polyhedron. Yeah. Sorry, I use words wrongly. I hope it's clear what I'm trying to say. Okay, Is that clear? So we want to prove this. So what do we want to prove? Somebody gives us a polyhedron. By that we mean somebody has given us an equation, yeah, of the form AX. So what sort of an equation have they given us? Or let me say AX less than or equal to B. AX less than or equal to B has been given. Okay. And we are going to generate from that. Yeah. Sorry, what is happening? Oh, I'm so sorry. This is not the lecture notes. Just 1 second. I seem to have destroyed everything that I did. Is this new? And then that's it. Oh my God.
No, Giacomo, you had a lecture 8 also in the, yeah.
That's what I'm looking at.
No, you're looking at 7, aren't you?
Oh, no, I just looked at, this is lecture 8.
I see.
And I have completely destroyed something. I don't know what I did. Oh my God. Okay. So life is going to be messed up. How can that be? 1 second, let me look at lecture 7 if everything is lying there. It's just wishful thinking. Oh, it is here. Okay, so I somehow mutilated lecture 7. Okay, wonderful. I mean, somehow this gives me some relief. Okay, yeah, so I seem to have destroyed lecture 7 and overwritten it by lecture 8. But never mind, for it shouldn't concern you. Okay, good. So how are we going to prove this? Okay, how are we going to prove this? So the way we are going to prove this, so what are we trying to prove? We are trying to prove that suppose P is a polyhedron, then it can be written in this form. A convex hull of a finite set of points plus a polyhedral cone. A cone defined by a set of inequalities. Okay. Now, how are we going to do that? Okay, so here's what you do. So you embed this polyhedron that you have been given in one dimension more. Okay. Yeah. So I've drawn a picture. I don't know if you are seeing the picture exactly the way I'm seeing it. So what have I done? Originally, I was in RD. Now I am in RD plus 1. And in RD plus 1, I take this plane, which corresponds to this axis being at 1. Yeah. So the extra coordinate is at value 1. Okay. And there I draw this plane, which looks like R to the power D. And in that, I just draw this poly. Is that clear? Just wait. On the other hand, look at this, and you. So the polyhedron that you have may be of one of these kinds. I've just illustrated both of them. Okay. In this case, it will start looking like this. But we are going to prove everything using cones. So which cone am I talking about? Okay. So I'm going to explicitly describe the cone. The cone that I'm going to talk about is AX minus lambda B less than or equal to 0. The polyhedron I was given was AX less than B. Okay. I'm sticking in, it was AX less than or equal to B. I'm sticking in lambda on the right hand side. Okay. And moving it to the left and writing it like this, and lambda greater than 0. Okay. So what does this object look like? In this case, it looks like you take this old polyhedron and you complete it as a cone. Yeah, you take this origin and you complete it. And if you think about it, the equation for that will be like this. Okay. In general, so we will use the same recipe. You have been given a polyhedron, which was of the form AX less than or equal to B. You stick in a lambda on the right hand side and set that lambda greater than or equal to 0. Okay. Now you can check that the set of points which satisfy these inequalities, yeah, these inequalities, the original inequalities plus this one, yeah, they form a cone. Yeah, if you scale any solution, so the points now look like this. Okay, x comma lambda. So if you scale any of them, it will continue to satisfy this. Okay, so yeah, good. Now there's a slight difference between this case and this case in the way I'm describing it. If you took this polyhedron and you converted it to a cone, this on the bottom plane corresponding to lambda equal to 0, you will only get a point. Yeah. So should I say that again? So suppose we are in 2 dimensions. So the original polytope, original polyhedron was, let's say, this infinite ray in 1 dimension. Now I'm going to go into 2 dimensions, place this ray at lambda equals 1 and generate the cone. So which cone am I talking about? Well, if I just use the recipe, that is, you join every point in the original one with the origin and do this, I will get a slightly funny cone. I will not quite get this line. Okay, so I shouldn't do that. I should actually, it will be sort of open on this side. Okay, so that is not what I'm talking about. Please don't go by the intuition, go by this equation. Okay, so in particular, when lambda is set to 0, yeah, we will get an equation here which looks like AX less than or equal to 0, because this lambda has become 0, which will be a cone. So that is the cone that is here. Okay, so the new cone that I have generated, it has an intersection with this plane, with the plane corresponding to lambda equal to 0, and that is this cone. Okay, is this clear? So I have still not proved anything. I'm going to use the theorem about cones, that is, finitely generated cones and polyhedral cones are the same object. There was equality. That theorem I'm going to leverage to prove this theorem. Okay, so first I have to convert my situation into cones, and I do it completely algebraically by saying that whatever equation you had to begin with, you add a lambda to it in this fashion. Is this clear? But intuition is this, that is, you place the old cone at lambda equals 1. Is that clear?
Yes.
Yeah, okay. So now, so as I said, this now becomes a cone, and it's a polyhedral cone, but we have already proved that polyhedral cones are the same as finitely generated cones. So there is a finite set of points, now points in Rd plus 1, which generate this cone. That is, depending on your example, this cone or this cone are being generated by these. Now, look at this, and you just normalize these vectors so that the second coordinate is 1. Okay, lambda was greater than or equal to 0 anyway. If lambda is 0, leave it as 0. If lambda is any positive number, you just scale it so that it becomes 1 here. It will still be in a cone. So we might as well assume that the generating set looks like this, where each lambda I is either 0 or 1. You collect those which have lambda 0, collect those which have lambda equals 1, and separate them. The intuition is those that correspond to lambda equals 0, yeah, they are the generators of the cone that you are looking for. And those that have 1 in their second coordinate, yeah, those that have 1 in the second coordinate, they are points they are these rays. So you restrict themselves, drop the last coordinate, and you have got a finite set of points, and they will generate this what is this finitely generated convex hull. Yeah, a convex hull. And those that gave you lambda equals 0, you just knock off their last coordinate. Yeah, and that forms the cone, and that cone is the C that you want. So what is this? So you set your Q, the convex hull that you wanted, you extract it out of this solution which came from the previous theorem, last time's theorem, by knocking off lambda where lambda is 1. And from the remaining, you knock off lambda where lambda is 0 and check that every point of your polyhedron now is generated. So if you have a point in this polyhedron, well, yeah, so this polyhedron is precisely this cone where lambda has been set to 1. If lambda is set to 1, this inequality already holds, and the set of points which satisfy this inequality are precisely the old polyhedron. Yeah. So let us see how lambda, the second coordinate, is going to become 1 in any such, whenever something is generated out of this. Well, the zeros, don't have to worry. You can add any positive combination of these, and that's not going to affect the second coordinate. If the second coordinate has to be 1, you have to take a certain combination of those points here which have lambda as 1 here. And the only combination you can take is a convex combination, because their average, the sum that you assign here, yeah, all these are 1. Yeah, so the sum of those weights, your multipliers, must be 1. In other words, you are taking a convex combination. So you are taking a convex combination of these xi's. Any point in this is generated by these. So to generate such a point, you must be taking a convex combination of those points which have lambda equals 1 and adding an arbitrary conic combination, a non-negative combination of the other vectors. That is to say, every point in that polyhedron is obtained by first taking a point in the convex hull and adding to it an arbitrary point in the cone. Is this clear? All right. Something happened. Yeah, you took your old polyhedron, embedded it one plane up, but did everything algebraically. Yeah, and you appealed to the theorem from last time. Okay, just remember these things and try to reconstruct it yourself. The other direction. Suppose somebody has already given us a decomposition of some set in this form. Okay, so that is Q is already a convex hull of some points and C is a cone, and they have given you both these things. So what have they done? They have given you, actually you should look here later. Yeah, look on this side first. They have given you a Q and they have given you a cone. Yeah, a cone. You know, I've drawn it in this funny way because I'm going to do some gimmicks. Yeah. So basically, your actual polyhedron is this P. Yeah. This P is actually obtained by what happened? Just you sum this. Yeah. You are supposed to add this cone everywhere, but you see what it is turning into this space. Yeah. Yeah. So you took a cone which I have destroyed, which used to be here, and you added that cone to every point of the original polygon here, but in general a finitely generated convex hull of a finite set of points. Okay. Now I would like to describe this object which I have got here. Yeah, this object. Yeah. Yeah. This object by a system of equations. Yeah, they have given me this. How do I generate it? Using a system of equations. Where will I get my system of equations? I will get my system of equations by by appealing to the theorem from last time, which tells me how to go from generators to system of inequalities, not system of equations, system of inequalities in the case of cones. But now I have one cone and a convex hull sitting on top. So what do I do? So I generate this. One second, let me explain. Yeah. So look at this. So I artificially define a cone now. What is this cone? You take all these points, yeah, and add a one in the second coordinate, which is to say you embed the old convex hull at one level above the origin, yeah, in the direction lambda. Okay, and the old parts, the old cone, you don't lift it up, you leave it here. Is that clear? The old cone which was given to you, you leave it on the floor, you raise the convex hull to the ceiling, okay, and just say that here is a bunch of points, yeah, and consider its cone. So it will be some funny cone, yeah, I mean, it will be generated like this, but automatically all these things will come up because you are generating with this, yeah, so some object will come up here. But it is a finitely generated cone. So that finitely generated cone ought to have an inequality. It is also a polyhedral cone because of the theorem from last time. So it must have this representation. And now, in this representation,
here lambda is a vector, right?
Sorry, lambda is a constant. Lambda is a variable now. This has d variables. This is one extra variable.
Okay.
If you are you are right, I should have probably written it on this side. Yeah. So my matrix looks like A followed by this column B. Yeah, A followed by B, and then maybe there is an X and a lambda and less than or equal to 0. So it is an honest set of inequalities with right hand side 0. That's what I mean by this. Okay, yes, thank you. Yeah, I should probably write lambda on this side, but you understand. Lambda is a scalar variable, B is a vector of scalars, but those are fixed scalars. This is a variable. Okay, now you can see that if you look at this cone and all the points of this cone, if you take the intersection of that cone with the ceiling, with this affine plane, that is precisely, and you drop off the last coordinate, that is precisely P. Yeah. All those points that can be generated out of these, a convex combination of this, which means the second coordinate stays 1, and you can add anything from here. So now that we have got our hold of this equation for the cone, which is a much enlarged object, we can restrict that cone to lambda with lambda equals 1, and we get this inequality. So what have we proved? That somebody gave us a polyhedron in this form as a sum of this. Yeah, so they gave us some convex object which is a sum like this. We can obtain, or there is a set of inequalities which describes the very same object. Yeah, so P is a polyhedron. So this is, so every polyhedron can be described in two ways. Either you write the equations, or if you can't write the equations, there will be a convex hull and a cone, just these two objects, and it's just somehow decomposed into these forms, and that's why it's called the decomposition theorem. So now the main theorem of Politico. Okay, so this is what you are familiar with. So suppose P is a convex hull of a finite set of points. Now we are getting closer to what Srijato asked. So if P is a convex hull of a finite set of points, okay, so now it fits into this framework where this cone is the cone consisting of the single point 0. Okay, so if P is a convex hull of this kind, then P is a bounded polyhedron. Convex hulls are already bounded, and anything which can be written as a convex hull plus a cone is always a polyhedron. So in particular, if it is a convex hull plus the zero cone, it is also a bounded polyhedron. Yes, because it's a convex hull, it's bounded, and because it's the sum of a convex hull and a cone, it is a polyhedron. That is, it can be described by a set of equations. So we have proved this direction. Okay, and in this direction, P is a polyhedron, but we know that any polyhedron is a convex hull of a set of points plus a cone, but it is bounded. If it is bounded, that means the cone must be the zero cone. Okay, so P is a convex hull of a set of points. So it is very cheap. Once you have proved the decomposition theorem, yeah, it's a slight generalization of the main theorem of polytope theory. Okay, that is, when you have a set of equations in any dimensions, yeah, and if the object that you get is bounded, then there are finite number of points whose convex hull is that object. But in general, if you just have some inequalities, then you will get a polytope or a convex hull together with a cone, yeah, and they form the entire object.
So the decomposition P equals to Q plus C, is this unique or
Not really.
up to trivial transformations?
Yeah, I don't know what you mean by trivial transformation, but say, for example, so I don't know if I will be good at drawing this. Let me try. Sorry, I can't draw it. So I'm in a book. Yeah, so imagine that you have this roof-like object, and everything under this is your polyhedron. That is, you just take two planes in 3 dimensions. Yeah. So if you take two planes, this is the roof of, yeah, and just extend it like that. I don't know if you're seeing me, but
Yes.
that's a polyhedron. Now, the theorem says that it is a sum. Yeah. Okay. So, but in this case, it is a cone itself. So yeah. So is this unique? I have a suspicion that. Yeah, I'm not sure. Okay. Yeah, I'm not sure it is unique. The cone part is unique, but I don't know if the part in Q we can play around a little bit, maybe. I'm not sure. Okay. Yeah, probably. Yeah. I thought about it, but now I'm getting confused. I'll tell you later. Okay. Okay. So the next thing I wanted to do, yeah, and I'm running a little bit out of time, but let me do this part a little quickly. Yeah, but you can ask and stop me. Yeah. So, okay, so this is all I wanted to say about the decomposition theorem. Okay, so I just wanted to say one thing about LP duality again. Okay, so LP duality is closely connected to our fundamental theorem of inequalities. Okay, and in this way, so suppose you have a prime, so the LP duality can be derived from the fundamental theorem of inequalities like this. So suppose you have an LP, yeah, now it is in slightly different form, not the equational form, and it achieves its optimum here, yeah, at this point, yeah. And now look at all those inequalities here, which are now satisfied with equality. So some of these inequalities have become tight at this point. Presumably, if none of them is tight, then we could have moved the point slightly in the direction of the objective function. So some of those inequalities have become tight. Okay, just focus on them. There are these R inequalities. So X star is the optimum. There are these R inequalities which are tight. Okay. Now the claim is that look at the normals to those inequalities. Yeah, those are the outward normals. The normals, yeah, normals like this. Yeah, The claim is that your objective vector, the vector that defines the objective function, is in the cone of these points. And the reason is that, so this is the claim. When the optimum happens, look at all the tight equations. Locally, the object here is looking like a cone. Huh? Don't go too far. Just look at the local situation here. It looks like there is a cone going on here. Okay. Later on, some other constraints may be cutting them off, but there is a cone going on here. So locally, there is a cone, and that is the cone I have. Yeah, but I'm now talking about the cone of the normals. Yeah, so this is the cone of the normals. Yeah. Okay. Now the claim is that your objective function better be trapped here, because if it was not trapped here, then there is, by the fundamental theorem or Farkas lemma or any of the other things or common sense, there is a hyperplane defined by this normal which separates those normals and C, the normals to these equations and C. Is that clear? Then if you perturb this point x star by x prime in this direction, yeah, so you obtain a new point which is x star plus a little epsilon times x prime, that is, you move in this direction. Then what happens? What happens to the objective function? The objective function at this new point, yeah, so I'm proving this claim. I'm proving this claim that if this was the optimum solution, then this objective function better be trapped here, because if it was not trapped, then I'm sorry, what am I? Yeah, if it was not trapped, then if you look at the objective function at this new point which I've constructed, it will be the old objective function plus this. But x prime's dot product with C is strictly positive. Yeah, it is strictly positive. So at x prime, your objective function is, what did I say? Yeah, is even greater than the objective value at x star. Sorry, at this point, x star plus epsilon x prime, your objective value, yeah, at some point here is even better than this, which is a contradiction. So we know that this objective vector, the vector C, yeah, that must be trapped in this cone. Now, if you see, so, okay, so is everybody okay with the claim? If that objective value was not trapped in these normals, we would have been able to improve the optimum. Okay, so we are assuming that the primal has an optimal solution, and we want to show that the dual has an optimal solution and also has the same value. Okay, so let us see. Write down this objective vector in terms of the normals. It is in the cone, so we can write it as a non-negative linear combination, as a conic combination of these normal vectors. Now, multiplied by x star on both sides. What do we get? These are tight inequalities. So A1 transpose star times x star is beta 1. That is the component of the vector B. A2 x star is beta 2. You remember? These are the equations that are being satisfied. They are tight. Okay. So if you take this dot product, it is equal to this scalar. So you write them down. Okay. And what you see is that the primal optimal was x star, because that was the definition of x star, but it is equal to this, and it is a linear combination, yeah, a non-negative linear combination of the right-hand sides of, yeah, ax less than or equal to b. Okay, that means you have found this lambda actually constitutes a solution to the dual linear program. Okay, so you have found a solution to the dual linear program which matches the solution to the primal. Yeah, and we already know by weak duality that the dual could not have done any better. Okay, so this must be equal to the optimum. Okay. So let me just yeah, is this clear? Yeah.
But why is this a physical interpretation?
Sorry, why is this a feasible solution? The
You
lambdas?
said this is a physical interpretation of LP duality.
Sorry, this is a
You wrote in the notes above that this is a physical.
physics. Oh, sorry, the physics. Yeah. So the point is that if you look at the book also, it looks like there is some sort of a force C, which is trying to move your objective solution. Think of it like a ball, and it is trying to move the objective function in this direction. So there must be some normal forces provided by these planes, which is keeping the ball in position and not allowing it to move further. Okay. So yeah, you can think about it like that. It is because of these normals which are providing force in the opposite direction. Yeah, they are trying to keep it on this side, that it is not moving. So the reason that this when you have a plane and a body, the only force that plane provides on the body is in the normal direction. If these normal directions together are not able to counteract this force, the body will move towards that force. Yeah, and the fact that it is not moving means that this force must be trapped in the normal directions of the planes that are currently keeping the ball in place here. Okay, so it's just nothing serious. Yeah. Okay, so in the next about 25 minutes, I want to tell you a theorem of Tverberg. And but if there are any questions about this part, yeah. So we are finishing with duality, yeah. And is there any questions? Please ask. So what have we done today? Yeah. So we had So we had the decomposition theorem. From the decomposition theorem, which was for Polyhedra, we obtained the theorem for polytopes. That is, polytopes can be described in two ways, yeah? Either by intersection of half spaces or as convex combination, a convex hull of a finite set of points. And I also pointed out that the theorem about separation theorem, that is, whenever something is not in a cone, then there is a separator, yeah, defined by a normal, that leads immediately to the strong duality theorem. Okay. Now, so what we are going to do are some theorems about convex geometry. Okay, not directly related to linear programming, but these are really beautiful theorems, and you will hear about them from other people. So I just wanted to make you a little familiar with them. Okay. So there is a theorem called Karat-Theodoris theorem, which, let me just explain, in 2 dimensions. So right now you think of this as 2 dimensions, and here is some polygon, and there is a point inside the polygon. That means this point is somehow a convex in the convex hull of these points. That is, it is it's a convex combination of these points A1 to AN. X is in a convex combination of A1 to AN. Okay. But from our intuition, you can always triangulate any polygon. Yeah, any convex polygon or any polygon, actually, you can triangulate. Then this particular point actually is a convex combination of 3 of them. So you might have a polygon which has a millions different vertices in it. But if you take any point inside the polygon, its presence in the polygon is already justified by 3 of the vertices of the polygon. Yeah. So M was 2 and you needed 3. Karat-Theodoris theorem says that this is true in general. So suppose you are in, now my M and D are all messed up. Should I just change this? Yeah. So if you have a point in the convex hull of A1 to AN in M-dimensional space, yeah, but the number of points is huge. Yeah, it's a convex hull of a huge number of points. and you have a point inside, yeah, it's in the convex hull, then you can find at most m+1 points, which already describe this, whose convex hull already contains this. Okay, so this is related somehow to that fact that separating hyperplane touches the cone in a space of dimension m-1 described by those m-1 vectors. But that derivation is not straightforward. But there are other simple derivations of Karat-Theodoralis theorem, and it will be in your homework. Okay, so you will have to prove Karat-Theodoralis theorem in your homework. But let us assume it for now. That is, in m dimensions, if you are inside a convex hull, then you don't need all the points, all the vertices. You need only m+1 of the given points. Okay, and they alone will generate everything, generate that point. Yeah. For some other point, there'll be some other subset. Yeah. So if you take the point here, then probably this, and this generate this point. Yeah. If you take this point, maybe this, and this generate this. Every point is generated by 3. Yeah. In R2, in M, at most m+1. Yeah. I say at most m+1 because sometimes you might have a point like this point on the boundary, in which case you need only 2 and not 3. Now there is a far deeper theorem called the colorful Karat-Theodoralis theorem, and my goal is to tell you about what is this colorful Karat-Theodoralis theorem, and then we will see a beautiful application of this theorem to prove theorem of Tverberg's. Okay, so everything. So I mean, please just relax and watch the pictures and listen to me. Yeah. So what is colorful Karat-Theodoralis theorem? Instead of one set of points, instead of one polytope, yeah, polytope means a bounded polyhedron or a convex hull of a finite set of points. So instead of being given one convex hull, we have been given d+1. Yeah, so there have been d+1 sets, S1, S2, SD+1. So for example, here, each of them you should think of as a different color. So the points here are S1, S2, and these are S3. Yeah, the green points are S3. Okay. So in general, you are in d dimensions and you have been given d+1 sets. Okay, d+1 sets of points. And if you look at the convex hull of each of them, there is a common point which is in the convex hull of all of them. So here is a point which is in the convex hull of the red points. If you take the convex hull of the red points, it's inside. If it's in the convex hull of the green points, it is inside. If you look at the convex hull of these purple points, it is inside. So it's a point that is common to the convex hull of the red points, the green points, the purple points. Yeah, all of them. Then that very point, yeah, so first of all, by ordinary Karat-Theodoralis theorem, this very point is generated by some d+1 of these red points and d+1 of these green points. That is true, yeah, by ordinary Karat-Theodoralis theorem. But what does the colorful Karat-Theodoralis theorem say? You want to read this yourself, then I will say it. Read this part. If it is the case that there is a point which is in the intersection of these convex hulls, that very point can be obtained by picking one green point, one red point, and one purple point and taking their convex hull, and X will be inside. Yeah. Those points which generate X are colorful. Every color, each one of these d+1 colors appears in it. This is a theorem, and this is called the colorful Karat-Theodoralis theorem. Is this clear?
Yes.
Yes.
Sorry, everybody?
Yes.
Okay. So I'm going to call people. Ashutosh, is this clear? What is being claimed? not clear. Ashutosh is there. Shomajit, is this clear? He's also not there.
Yes, sir. Yes, sir. Yes.
It's clear. Yeah.
Yeah. Fine.
Yeah. It is. Yeah. It is colorful. Yeah.
Yeah.
These points are of different colors, and this point can be when it looks around and sees who is generating me, it sees all the colors. Okay, but one of each. Yeah. Okay. So now we are going to use this theorem. I will tell you later how to prove it. Yeah. We have about 25 minutes, and just concentrate. Okay. So now this is Redon's theorem, which I did. Arkadev do this in your course in the mathematical foundations for computer science? No, this time we didn't do it.
No.
Okay, doesn't matter. But we are going to do it now. Okay. So suppose you are given d plus 2 points in d dimensions. You are given d plus 2 points in d dimensions. Then these d plus 2 points can be split into a subset and its complement. Yeah. So these d plus 2 points can be split into a set of points and the complement. So they can be split into two parts. So that if you take the convex hull of the first part, those which are in the set S, and those which are in S bar, they will have a point in common. For example, here I was given 4 points. Why was I given 4 points? D was 2, and I am supposed to be given d plus 2 points. So 4 points. Here were 4 points. I can split it up into 2 sets. This and this, no, their convex hulls don't meet. It's always possible to split them up into 2. Pair this up and this, and look at the convex hull that contains this point. There is a point in common. Yeah.
So you have written the convex hulls are equal.
Sorry.
No.
Oh, sorry. Yeah, maybe. Okay, so suppose the 4 points were these. What would you do? So let us see if Redon's theorem holds. Why does Redon's theorem hold for this? Which pair of convex hulls intersect? Yashwant. Can you find a set of points S out of this and its complement? And if you take the convex hull of S and convex hull of its complement, they should have a point in common. Yashwant, can you think of this? Should I give names to these points? P1, P2, P3, P4. Tell me. Is there a set S?
1, 2, 4.
That's right. Yeah. So Yashwant, yeah. So take this, and this and call it S. This becomes S bar. The convex hull of S bar is just the single point itself, and the convex hull of these 3 also contains it. Yeah. You have to be, so it's not that these are of the same size or anything, even in 2 dimensions. Yeah. So in this example, this worked. But this is a theorem that is true in any dimension. If you take enough points, d plus 2 points, you can split them up so that there is a point which is common to both of them. Okay. And why is this true? And this is again our familiar trick. I don't know what I did here. There should have been a +1. Yeah. You take those d plus 2 points and put them on the ceiling. Put them on the ceiling, which means to each of them, you add this coordinate, 1. Yeah, you have placed all the points on the ceiling. Now, how many points do we have here? Sorry, how many points do we have here?
D plus 2.
D plus 2. In what space?
D plus
R power
1.
D plus 1.
So they must be linearly dependent. So let us look at the linear combination that arises, which gives 0. Okay. This is a non-trivial linear combination. So there must be a lambda, which is positive. Yeah. Which is, yeah. So, and notice that the last coordinate has to become 0. When I say 0 here, I mean 0, a vector 0. which means there must be a lambda which is positive as well as a lambda which is negative, because otherwise how did the last coordinate cancel and become 0? Okay, so it's clear what we should do. Look at all those points where the lambda is positive. Yeah. And look at all those points where the lambda is negative. So that is S bar. So the positivity and the negativity tells you which side to go. Positives go into S, everybody else goes into S bar. And we know that they nicely cancel each other. So if you take this combination, those which were positive and those which were negative, and take them to the other side, so there is a minus sign, yeah, they are both equal. Yeah, look, we wanted S and S bar so that their convex hulls have a point in common. We seem to be going in that direction. There is a point which is generated by the SS. There is a point which is generated by the S bars. Yeah, there are these ugly sticking ones which we need to remove. Yeah, but what we want seems to be holding. Now, if such a thing holds, then the xi's themselves must match. That is, if you take the lambda I xi and the minus lambda j xj, they must be equal. But this was what I said earlier. There should be cancellation of the scalar. That means the positive lambdas and the negative lambdas, yeah, must add up to the same thing, yeah, in absolute value. Yeah, that means if you look at all these coefficients here, which are also positive, all these coefficients here are positive, and their sum is the same. This is not a convex combination, because these lambdas could be huge numbers, 50, 90, 23. Yeah, but we need to normalize them. But the normalization factor that you will use on the two sides is going to be the same. And that is because you somehow set it up so that the normalization factor becomes the same. Okay. And once you divide this, this looks like an honest to God convex combination of these xi's. This looks like an honest to God convex combination of these xj's. So we have proved Radon's theorem. Sorry, I did it a little fast. Idea? Go one dimension up. You still, yeah, have more variables than equations. You are in D+2. You have D+2, yeah, positions, whereas you are in D+1 dimensional space. And then you convert this linear dependence into what you want. Okay. Yeah. Do it yourself. Tverberg's theorem. What does Tverberg's theorem say? You have some m points. So now what we want is, instead of two sets, we want n sets. So we want to say, how many points must you give so that I can partition the points into n parts, not two parts. Two parts is Redone. I want to divide the points, partition them into n parts, so that if I take the convex hull of the first part or the convex hull of the second part or the convex hull of the last part, there is a point in common. They all have a point in common, just like here they had a point in common. Now we will have many sets, but n of them, so that they all have a point in common. Okay. And the answer is that if you take m to be this number, yeah, instead of D+2, you take this, then this will be true. And one can check that if you just took this much, yeah, it's not completely obvious, but if you took this much, then it won't be true. Yeah, just like if you had only 3 points, it was not true in 2 dimensions. In particular, if you set n equals 2, you recover Redon's theorem. Okay, so this is a generalization of Redon's theorem for arbitrary n, and it's a, yeah, maybe at first sight a strange looking formula, and this is the theorem, and this is Tverberg's theorem. Okay, now, okay, so if you have a generalization of the theorem, there must be a generalization of the proof. So let us think, yeah, quickly. Yeah, so how will we do this proof? So the way we will do this proof is, and now we get stuck. Redon's theorem, we used positive and negative numbers. Now we want n different signs, and nobody in mathematics has ever taught us there is positive, negative, and some other tiv, and some other tiv, and there are n different signs. Yeah, and it looks like that is demanded by this problem, or at least the intuition. And Sarkaria, this is Professor Karanveer Singh Sarkaria from Punjab University. So this Tverberg's theorem was proved in the 1960s, and it had a complicated proof which would take 6 hours to present. And Professor Sarkaria just generalized Redon's theorem in the right way and used the colorful Karat-Theodoris theorem, which was also observed by Tverberg later. Tverberg gave a shorter proof using colorful Karat-Theodoris theorem, but that was still quite complicated. But the proof that I'm going to present now is Sarkaria's proof. Okay, so what does the Sarkaria do? He says, first of all, take your points. Yeah, I have purposely called them x1 hat, x2 hat, xm hat, where m is this number, and put them on the ceiling. Yeah, so now you are living in which a space of dimension d plus 1. They were originally in d. There is d plus 1. Okay, so at least the number d plus 1 seems to be showing up. Yeah, what linear algebra argument will give us this number? So first check that. He says, so now I've got d plus 1. Now what you do is, I don't have signs, but notice that in one dimension, what's a sign? Let me just see. There is a plus 1 and a minus 1, and these are the signs. So these are two numbers which themselves are linearly independent. Like each of them is a non-zero vector, but their sum is 0. So Professor Sarkaria observed that actually that is the main property that we need. So look at what he has done. He says, let me take a vector space of dimension n minus 1 and construct some n vectors with the property that they are all linearly independent. I mean, any n minus 1 of them are linearly independent, but if the last one is actually the sum of the first. Sorry, the sum of all of them is 0. Okay, so let me not say this in abstract. W1 is this basis vector, which has 1 in the first coordinate and 0 elsewhere. W2 has 0 in the first coordinate, 1 in the second coordinate, and 0 elsewhere. These are the standard basis vectors. And Wn, what am I doing? This is n minus 1. Yeah, and this is n. Yeah. Yeah. So you take the first n minus 1 vectors. We are in this space. So we take the first n minus 1 vectors, and the nth vector, we just take the negative of their sum. Yeah. So you can check that the only dependency that holds among these vectors is that the sum of these vectors is 0. The sum of the vectors is 0. Okay. Good. So now what? Yeah. So we've got a space of dimension d plus 1 and a space of dimension n minus 1. And we are going to work in a space of dimension d plus 1 times n minus 1. How? Consider all matrices which have d plus 1 rows and n minus 1 columns. Yes? What is the dimension of this space?
D plus
Space
1
of
n
all.
minus 1.
Sorry, say that again.
D plus 1 n minus 1.
Yeah. So now we seem to be in this space. And what have we been given? We have been given these many vectors. That means one more than the dimension of the space. Things look familiar? If you have one more than the dimension of the space, then you have a non-trivial linear combination, and maybe something will go for us. Yeah, something might work out. Okay. Yeah. So now we are ready to apply the colorful Karat-Theodoris theorem. And how do we do that? Okay, you recall that there were these vectors x1, x2, and xm. What were x1, x2, xm? These were the original vectors raised to the ceiling. Yeah, x1 is the original vector raised to the ceiling. Yeah, Now you take the product. So this is a matrix. Huh? You take X1 transpose W1. Yeah. That matrix you write here. X1's outer product, you can call it. Actually, you can, the way it is usually done is in tensor product. I'm not using the word tensor. You just construct these matrices. X1 times, sorry, what did I say? X1 transpose. Which one? Which did I do this? Did I mess this up? Of course I messed this up.
It will be XW1.
X1 W1 transpose. I never do this right. I will not correct everything. I'm just going to correct this. Yeah. Yeah. Everywhere, please, son, there is no transpose here. There's a transpose there. Okay. I will correct everything in the notes. Yeah. So you take X1 W1 transpose, X1 W2 transpose, X1 W3 transpose. Those are the vectors here. Okay. And so these are of one color. Yeah. I don't know, maybe this color. And these are of another color. These are all. So these are how many colors now? M, one more than the dimension of the space. That is what colorful Karat-Theodore theorem asks. Colorful Karat-Theodore theorem asks for a collection of points with dimension one more than the dimension of the space. Yeah. Okay. Yeah. I'm so sorry. Yeah. But please, all the transposes are on the second, not the first. I just don't know what I do. Anyway, now, okay, but to apply colorful Karat-Theodore's theorem, there must be a point which is common to all these convex hulls. So why do we know that there is a point which is common to all these convex hulls? What combination of these do you want to take? I mean, the first coordinate is always x1. So what combination, what can you do to these vectors? You are supposed to multiply them by some scalars and add them. What scalars occur to you? What scalars should we use?
What we going to do the definition of WI?
Sorry?
WI.
Sorry, what did you say?
Sorry, what was WI?
Oh, W's were these fake signs that Sarkaria invented.
So their summation will be 0. The 0 is in the convex hull of each of them.
Correct. If you add all these vectors, they look like x1 multiplied by the sum of the Wi transposes. But the Wi's all add up to 0. So the 0 matrix, yeah, if you take the average of these matrices, it will be the 0 matrix. The average of these matrices is also the 0 matrix. The average of these matrices is also the 0. So the point 0 is common to all these convex hulls. Okay. So, yeah, so each point is a d+1 times n-1 matrix. We are living, and the number of sets here is one more than the dimension of the space. So there is, and we also know this because Sri Jato told us which point to look. If you look at the 0 point, 0 is in each of these sets. The 0 matrix is in each of these colorful sets. And colorful Karat-Theodore says that that very 0, the matrix 0, this is the matrix 0. The matrix 0 can be written, yeah, as yeah, as a combination. The 0 matrix can be written as a combination of one point where x1 is here and another point where x2 is here, xm here, because these points have color gray. The remaining, all these points had color. Anything which has x2 in the first coordinate, it has color green. So this is a gray point, a green point, and maybe a blue point, something like that. One of each, one x1, but the same W might appear multiple times. Please compare. This was the situation at some point in the proof of Redon's theorem. And we then segregated elements based on signs. Those that were positive, we put in one bucket. Those that were negative, we put in another bucket, and so on. What should we do now? These are our signs. Yeah. Those that use W1, which W1? The very W1, this W1. Those that have W1 in their here, put them in T1. Those that have W2, those indices here, put them here. And those indices that have N, you put them here. Is this clear? So how many sets have we obtained? N. And why is it N? One for each sign. Yeah, Shrijato, go ahead.
Some of them can be empty.
Sorry?
Some of this can be empty, right?
We'll see. Yeah. So at the moment, some of them can be empty, but we'll see that they cannot be. Yeah. But actually, yeah, at the moment, they can be empty. Yeah. Let us see. Yeah. Okay. Yeah. Now, so this very sum, yeah, you collect all of them that had W1 as their second coordinate, and you write them here. Yeah. So you take every index in J, the corresponding Xj will appear with the corresponding lambda. Yeah. But they have W as their W1 as the second coordinate, W2 as the second coordinate, Wn as the second coordinate. Yeah. Is that clear? And this sum is equal to 0. Yeah. Okay. Now, the claim is that all these things are actually equal. Each of these coefficients actually is equal. This coefficient is a vector here. Huh? This coefficient is a vector. Yeah, it's like a column vector. These are actually transposes here, but I messed up. Yeah. So all these vectors are actually equal. And why? Well, because this W, the only coefficients that are allowed that make it 0, the only dependency was that the sum of the Wi's should be 0. That means all these must be proportional to each other. Let us see why. Yeah, so I mean, that was for scalars. So suppose there was some vector here, V1, V2, some Vn, and if you multiplied it with W1, multiply means with W1 transpose, W2 transpose, and so on, it became 0. Okay. Now, if these Vi's were oriented in different directions, I can always take a dot product with with some vector and make one of the coefficients go away and become 0, and I will get a dependency among the Wi's, which doesn't look like sum of the Wi's or a scalar multiple of this dependency. Okay, so let me let you figure it out. Yeah, so this already means that all these quantities must be the same. Okay, these vectors as vectors, they must be the same. Okay, and now, so that vector which must be the same. So this is clearly a partition. Yeah. So all these vectors must be the same. And so remember Redon's theorem, we also had this issue of normalization. So all these quantities are the same. This looks like a conic combination of the vectors, of the xi's which participated in T1. These are conic combination of the xi's that participate in T2, of those things that come from Tn. But what can we say about the normalization? Yeah.
The last coordinates must also be equal. So
yeah. So again, we use the same trick. These vectors are in the ceiling. What allowed us to claim that the normalization was the same in Redon's theorem? The last coordinate was 1. Here also the last coordinates are 1. And since the last coordinates are all 1, the sum of the lambda i's must be the same. Now you see that since at least, yeah, so okay, now so we just normalize them by that. Sorry, there was an L here. Yeah. And since all these vectors are the same, you normalize and we get this equality where xi hat is on the top coordinate and 1 is in the bottom coordinate. Now, if this is an equality among such vectors, you can drop the last coordinate and we get this common point. Again, my hats are missing. And we have proved Tverberg's theorem. Okay. So I suppose the question is, why can't these LJs, why can't these normalizing factor be 0? Okay. The point is, yeah, need to, yeah, so this was the question Srijato asked. Yeah. So this is a non-trivial linear combination. So all the lambdas are not 0. So there are non-zero lambdas. And then there was one argument we needed to make to claim that
No, each lambda is scalar and equals to 0.
sorry?
No.
Sorry, yeah, you are right. This is colorful Karat-Theodoris theorem. This is not linear combination. Okay. So this is actually a convex combination. Is that clear? Colorful Karat-Theodoris theorem says that this is a convex combination. Okay. So that means in particular, some of these lambdas are definitely positive. Yeah. So the corresponding sum where a positive lambda lands, yeah, that sum will have to be positive. But because by looking at the last coordinate, we conclude that all of them must be the same. So all the normalization factors are positive. In particular, these sums cannot be empty sums. Yeah. Okay. So all we need to prove is colorful Karat-Theodoris theorem. I have run out of time, but actually the proof is just this much. What should we do? Should we finish this or it will take me 5 minutes? Or should we just stop? This has become too heavy.
We can see the proof actually.
But we can save it for next time. You see?
No. I would like to see the proof.
You would like to see the proof.
Could you do it next lecture?
Okay. Yeah,
Okay.
I can. Should I do it next lecture?
Yeah.
I'll do it next lecture. Let me just take 1 minute and say what happens. Yeah. So you know the setup of the colorful Karat-Theodoris theorem. So you have been given this point X, yeah, which is in the convex hull of the red points, the blue points, and the green points. You say which is the point that is closest to the target point X, which can be generated in a colorful fashion. Okay. And you prove that this Y actually should be X. Okay. And it requires an argument which looks like this, and we will do that next time. So any questions? Yeah, so I wish I hadn't messed up with the transposes. Yeah. So I will correct it in the notes, but I would really like you to please, read the notes and understand this theorem. What is remarkable is that Redon's theorem had a notion of positive and negative, and it requires some sort of insight saying that if mathematics doesn't give me signs, I'm going to invent signs and see what properties those signs should have for the proof to go through. And to me, like, this was really a beautiful application. Yeah. It's what makes beautiful mathematics. All right, questions. Yeah, I'm sorry if everything is too heavy for you. It is partly because of the style of my presentation, but afterwards, if you read notes, if you get the time, spend about an hour on Tverberg's theorem, it will be rewarding, I can promise. Yeah. Questions?
I have some general question. I don't know if it is related or not.
Yeah, please.
So this looks like, can Redon's theorem, or maybe, I don't know, can it be related to VC dimension somehow? It looks like that we should be able, at least for linear spaces. I don't know actually.
Yeah, so whether, yeah.
Because we are able to find two sets which have two sets whose convex combination has an intersection. So we should not be able to separate them by some linear.
Yeah, we cannot separate them by a linear. Yeah,
linear
because they have a
function.
point in common. Yeah.
So can this be more generally related? Can these be related somehow more generally?
With VC dimension, yeah. So VC dimension, yeah. So there, every possible subset is realized, right? Yeah. So let's look at Redon's theorem itself. Just says that one part. Okay. Yeah, I'll have to think. Yeah, right away I'm not able to see.
Okay, sure. Yeah.
Questions? Sorry. So please, yeah. So we will.